Hello, my name is Tan Xiaowen, a biomedical engineering student from University Tunku Abdul Rahman. Today, I would like to share with you about my final year project titled Development of Wearable Rehabilitation Device for Wrist Finger Mobility Rehabilitation. My supervisor for this project is Mr. Chong Yu Zheng, and my co-supervisor is Dr. Chan Xiao Cheng. Let's proceed with the introduction. A hand rehabilitation device functions to actuate movement at the finger and wrist joints. They are commonly used for patients with stroke as a substitute for the repetitive task practice performed by physiotherapists. Most commonly, the device acts on the proximal interphalangeal joint, also known as the PIP joint, the metacarpal phalangeal joint, also known as the MCP joint, and the radiocarpal joint, which is known as the wrist joint. The movement that is commonly actuated is flexion and extension at the PIP joint, flexion and extension at the MCP joint, and extension at the radiocarpal joint. After literature review and market research was conducted, it was found that most rehabilitation devices only have one pre-programmed exercise protocol when it comes to the angular velocity that is generated by the transmission system. This would cause discomfort to the stroke patients with severe spasticity. In addition, many of them do not have sensors that measure the recovery progress of the patient. Furthermore, they are often costly, with prices that range around a few thousand ringgit, and some are heavy, with certain models weighing as much as 2.3 kilograms, which reduces the accessibility and portability of the device. Lastly, many of these devices do not have built-in safety design in their transmission mechanism to prevent the actuation of motions that exceed the static constraints of the hand. Therefore, the aim of this project is to design a hand rehabilitation exoskeleton system that could provide continuous passive movements to the finger and wrist joints and allow the patient to choose between different rehabilitation protocols as well as to review their recovery progress. To achieve this aim, 5 objectives were set. Firstly, to design and construct a transmission system that can generate coupled flexion extension movements at the MCP and PIP joints of 4 fingers and extension movement at the radiocarpal joint. This transmission system also has to actuate movements that respect the static constraints of the hand and does not exceed the maximum angular velocities that can be generated by the hand naturally. Moreover, this sensing system should be constructed to measure the maximum flexion angle at the MCP joint and the maximum extension angle at the radiocarpal joint that the user themselves can generate independently for recovery progress measurement. Furthermore, this rehabilitation system should cost less than 1,500 ringgit, and the sections that are attached to the hand should weigh less than 500 grams. Lastly, the user interface should be designed to enable the user to choose between 3 levels of angular velocity that is generated by the transmission mechanism and allow them to view their recovery progress. Let's proceed to the methodology. The project timeline was divided into 6 main phases. In the planning phase, market research and literature review was conducted. Next, the design and construction phase ran in parallel with the functionality testing phase to produce multiple improved iterations of the 3 main subsystems, which are the sensing, transmission, and user interface. After that, these subsystems were integrated together to form a complete rehabilitation system and subsequently tested in the next phase. Lastly, the results of the project was documented. This project was heavily inspired by origami, which is the art of paper folding. There is a general perception that origami is child's play and can only be utilized for aesthetic purposes, as you can see in the images here. However, origami theory has inspired many engineering designs such as miniature robots, forceps, masks, and hydrogel patches, which is why this project integrated origami theory into engineering principles in order to create a novel design for the hand rehabilitation device. This theory was incorporated into 2 aspects of the hand rehabilitation device, namely the transmission mechanism design and the inclusion of an additional functionality in the user interface to teach users how to fold origami models. The benefits of incorporating origami theory is that it allows the maximum angular displacements that can be generated by the transmission mechanism to be integrated into the structural design itself, thus promoting safety. Moreover, studies show that the act of folding origami models contribute to greater improvement of hand functions and dexterity of the patients. This is the design architecture for the hand rehabilitation system. There are 6 main components, namely the power source, sensors, microcontroller, user interface, actuators, and transmission mechanism. The power bank was used to supply power via modified micro USB cables. The microcontroller chosen was ESP32, and the Arduino web editor was used to program the ESP32. Next, an Android mobile application was chosen as a user interface and programmed via Android Studio. Moreover, the sensors used were two 2-inch flex sensors, while two MG995 servo motors were used as actuators. Lastly, the transmission mechanism design was inspired by origami string and Miura Vertex theory, designed in SolidWorks, sliced in Cura, printed with Creality Ender 3 3D printer using PLA filaments. For the transmission mechanism, it was inspired by origami string and Miura Vertex theory. From the best of our knowledge, this design is novel and has not been attempted before. Miura Vertex is a type of vertex that contains 4 intersecting creases, while origami string is a template that contains multiple Miura vertices. The origami string template that was specifically designed for this project contains 3 Miura vertices, V1, V2, and V3. As you can see here, they have 55, 45, and 30-degree angles respectively, so that when they align with the joints and the origami string is completely folded, the maximum flexion angle that will be generated at the PIP joint is 110 degrees, at the MCP joint is 90 degrees, and the maximum extension angle that can be generated at the radiocarpal joint is 60 degrees. Here, the origami string is lying flat. And here, the origami string is fully folded. And if you refer to this diagram, you can see that the maximum angle that can be generated at each joint. The origami string template was then modified to form the crease pattern of the transmission mechanism shown in this figure. This crease pattern will exhibit the same performance as the origami string template. This is a teaching aid that I created to show how the transmission mechanism works. You can download a PDF copy in the Google Drive file attached under the description of this YouTube video. Currently, the transmission mechanism lies flat. As you can see here, the servo motors will be attached to the side panels in this segment of the transmission mechanism. When the arms of the servo motor rotates upwards, the side panels would also move up. Force will be transferred to the subsequent segments of the transmission mechanism, and it would fall like this. This would generate extension at the radiocarpal joint and flexion at the PIP and MCP joints. When the servo motor rotates downwards, the transmission mechanism will move back to its original position, causing the radiocarpal joint to rotate back to its original position and the PIP and MCP joints to undergo extension. After 10 rounds of designing, 3D printing, testing, and modifying the transmission mechanism, this is the final transmission mechanism design, and it contains 34 separate pieces in total. This is the printed and assembled prototype. The mechanism contains 4 main segments. These segments are attached to the hand as shown here, and this picture shows the transmission mechanism fully folded. In terms of software design of the hand rehabilitation system, the microcontroller and the Android mobile application communicate with one another via Bluetooth pairing. For the hand rehabilitation functionality, when the user selects the rehabilitation mode on a mobile application, this information is sent to the microcontroller, which initiates the correct servo motor control protocol. There are 3 different modes. Each of them would actuate joint movement at different angular velocities. For recovery progress measurement functionality, when the user selects this functionality, the mobile application will prompt the microcontroller to start recording measurements obtained from the flex sensors. The microcontroller will then convert the digital signals into angle values, and once the sensing cycle is complete, the maximum flexion angle recorded for the MCP joint and the maximum extension angle recorded for the radiocarpal joint will be obtained and sent to the mobile application, which then displays it to the user. For the origami tutorial functionality, users can play YouTube videos embedded into the webview elements in the mobile application. Let's proceed with results and discussion. Here is the developed prototype. This is the transmission mechanism, actuators, microcontroller, power bank, and sensing glove that contains flex sensors. And here is a video that shows how the entire hand rehabilitation system works. Kinovia, a video annotation software for sports analysis, was used to measure joint angles and angular displacement generated by the transmission mechanism. The following figures are graphs that show the change of joint angles across time for 3 rehabilitation modes. It was observed that the transmission mechanism produces angular displacements with a range of around 25 to 30 degrees. This table shows the maximum flexion or extension angles produced, and we can see that none of them exceed the static constraints of the hand. The following figures are graphs that show the change in angular velocities of the joints for 3 rehabilitation modes. This table shows the maximum flexion or extension angular velocities produced by the transmission mechanism. We can see that none of them exceed the angular velocities that can be produced naturally by the hand. In addition, the angular velocities for the difficult modes are the highest, followed by intermediate and then easy modes, proving that the transmission mechanism can actuate at 3 different modes. This table shows the mean maximum angles measured by the sensing system and the mean difference between these angles and the true values. Excluding measurements for 0 degrees, the accuracy of this sensing system is similar to the results obtained in another study whereby the maximum mean difference was 5.1 degrees. Lastly, the cost of the system was calculated to be 231 ringgit, while the total weight of the transmission mechanism attached to the hand is 250 grams. Now let's proceed with the conclusion. To conclude, all the objectives were fulfilled because the developed hand rehabilitation device could generate extension at the radiocarpal joint and coupled flexion extension at the MCP and PIP joints, and these movements respect the static constraints of the hand. The device could also measure the maximum extension angle at the radiocarpal joint and the maximum flexion angle at the MCP joint, and allows the user to select between 3 rehabilitation modes and displays the recovery progress to the user. It is also cost-effective and light. Most importantly, this project has introduced a novel design which provided insight on how origami string and Miura vertex theory could be integrated into the transmission mechanism designed for the hand rehabilitation system. Thank you for your time.